group, and then these bands of adults looking after children, contributing the structure which can drive and change the expected patterns of age distribution and transmission that we'd expect to see in a population. Vaccines can have some other indirect impacts, and in particular on the timing of outbreaks of infectious diseases and the predictability, actually, of outbreaks as well. To illustrate this, I'm going to use my favorite infectious disease example, because I did my PhD on it, so of course it's my favorite, but it's also a very nice, clean example, because it's one of the few situations where we have a long-term, longitudinal time series of incidence of an infectious disease that we can understand very clearly using models not much more sophisticated than the ones you've been using already in the course. So measles epidemics globally demonstrate what's called an endemic epidemic pattern of incidence, although they endemically circulate within populations, and especially before vaccination, we saw these very large cycles of boom and bust epidemics in communities. So this is the weekly reported cases from the Registrars General's weekly returns for England and Wales from 1944 up to 1965, and particularly between 1950 and 1965, we saw these very regular 2-year pattern of outbreaks. There was a major epidemic followed by a smaller minor epidemic in the next year, then leading to a repeat of the cycle. So very regular 2-year, very predictable pattern of epidemics, very stable. I suspect everyone here knows about measles, but just to remind us about what it is. It's an infectious disease, which is a very characteristic red rash. That's amazing for epidemiologists because it means it's very easy to diagnose. It's quite specific. So where we are lucky enough to have case reports of measles, we actually have quite a high confidence in those reports. Symptoms include fever, cough, lots of other things. What makes it actually a particularly dangerous disease is not necessarily the infection itself, but the impact that it has on our immune system. So it essentially resets our immune system, and all of the immunity we had before is pretty much gone. And that can lead to a very high increase in morbidity in children that are infected, but also in a very high, significant rates of mortality, although that typically happens after recovery. Spread by aerosol transmission, thankfully no animal reservoirs, so it's a good candidate for eradication. Infection results in lifelong immunity to reinfection. In fact, vaccination as well gives long-term sterilizing immunity to reinfection. So our SEIR model is a really good description of measles dynamics. Exceptionally high reproduction ratio, we've said already. Acute infectious period, we've seen these distributions as well, the latent and infectious period distributions. Latent period of about 8 days, infectious period of about 5 days. Okay, we know all this. So really good starting point, and indeed about as far as you need to go with measles is the SEIR model. But you will have seen that if we take the SEIR model and we simulate the introduction of measles into a completely susceptible population, we will see a massive epidemic initially, and then over a longer time period, we'll see these damped oscillations going down to a stable, fixed point. Okay, that doesn't look anything like the measles time series in England and Wales. Okay, but there's this suggestion here of cyclic or oscillatory behavior. Okay, and it turns out that epidemic models are effectively mathematically the same as a simple pendulum or a simple damped pendulum. Okay, so if you imagine my arm is a pendulum, if I displace it from the equilibrium and let it swing, looks like I've broken the other arm now, but okay, never mind, I have to make do with this. but slowly wind resistance will cause it to come to rest at the equilibrium. Okay? But with a pendulum, we can put energy into it, and we can force it to oscillate as well. Okay? So there's a natural frequency for a pendulum, which is given by the length of my arm and the strength of gravity, local to Nairobi. It varies a bit. It depends what's underneath you. And when left to its own devices, it will oscillate at that natural frequency, dependent on my arm. But if I put energy in, I can force it to go at multiples of that frequency, in fact, arbitrary frequencies, if I put enough energy in. Okay? So when we have the tendency towards oscillatory dynamics, if there is some mechanism which introduces variation, then we can drive oscillations in epidemic diseases. Okay? The question is, what is putting in that variation? Okay? If we think about human infections, things that change seasonally are probably the most likely thing that could affect things. Things that you might immediately think of, is it climatic variation? Do diseases transmit more during the winter when people are crowding together? Is it the vitamin D that we get from the sun? There's lots of papers written on different mechanisms that could explain seasonality. For measles in England and Wales, there's a very, very clear signature. When we looked at statistical models to estimate how the transmission rate varies over the year, saw there was a very strong concordance between the variation in the transmission rate and the timing of the school terms. Okay, and this makes sense for measles. Mean age of infection was about 5 before infection. So pretty much you're born as a baby, you're susceptible, you're protected by the fact that you're not hanging out with many kids. First day of school, you run around the playground, you're spitting on each other, licking each other, it's chaos, and everybody gets measles in the first week, more or less. So there's this huge drive in transmission, this cohort effect when new kids entered primary schools, and then the transmission rate slowly declined over the school year. And we can even see dips for the various school holidays, in particular the long summer holiday. So this variation in transmission rates was sufficient to drive those dramatic patterns of cycles that we saw in the data. So we can finish our model, basically finish our model of measles vaccination in epidemiology by introducing, rather than having a constant transmission rate, having something that varies over the year. So the simplest assumption we can make is that it's a cosine function, so that's just something that goes up and down. We can maybe vary the phase as well, just to get it in the right place for the school terms. We can do a bit better for the England and Wales data, and we can just have a transmission rate which is high in the terms and low in the holidays. Okay? And characterized by some amplitude of seasonality, which is given by the difference between the high and the low values, or as a special parameter in the cosine forcing. Okay, so what happens if we put in some form of seasonal forcing? Well, if we tweak that amplitude of seasonal forcing just right, we can get, in a deterministic SER model, a very regular, spiky-looking 2-year cycle in incidence. Okay? So what happens when we introduce vaccination? Okay, so this is our roughly calibrated measles model with 2-year cycles, and then we introduce vaccination at 60% at the 10-year period here, and there's 2 immediate effects. Transmission immediately collapses, so this is what's sometimes called the honeymoon period for the introduction of vaccination. And that's because we get this double whammy impact that we've suddenly protected a lot of individuals and the transmission rate collapses down. If we look on a longer time period, we see that the 2-year cycles have extended out to, in this case, I think 4-year cycles for a period of years before then settling down to smaller annual cycles later. Okay? So the impact of vaccination is equivalent to changes in birth rate, but also it turns out to changes in transmission rates. So a very elegant paper by David Earn back in the 90s, which showed that you can actually predict the periodicity or the timing between outbreaks for measles epidemics by just looking at changes in birth rate and the proportion of the population, or the proportion rather of births which are vaccinated, so the vaccine coverage. Okay. And because of that clever relationship, it means to understand the dynamics of measles, we only need to look at how the periodicity, how the timing between epidemics changes as we vary the transmission parameter of the model. Okay, so we keep our seasonality constant. That's something we've sort of estimated from the data. And then we vary the mean transmission rate. Okay, and we see what effect that has on the timing of epidemics. Okay, so this looks like a horribly complicated and clever figure that got you a science paper, which it pretty much did for David. But it's not as complicated as it might seem. It's just looking at model behavior in a slightly different way. So what a bifurcation diagram, how this is created, is we run the model for a very long time for a particular value of the transmission parameter. And rather than recording the time series, we just strobe the model at a fixed point. So say on the 1st of January every year. Okay? And if we have annual cycles, then the incidence on the 1st of January will be the same every year. Okay? So we would get a point like this on the blue curve. All right? If we've got a 2-yearly cycle, then we will get 2 different values in the minor and the major epidemic years. Okay? And that's what we see in this region of the graph. Okay? So this area of the transmission parameter is where England and Wales was between the 50s and 60s. So we were in these stable 2-year epidemics, varying a little bit as the birth rate changed over time. Okay? And when vaccination came in, it pushes us down into this area of the bifurcation diagram. So this is called a bifurcation diagram because as you increase the transmission parameter, your stable cycle bifurcates into 2 to get a 2-yearly cycle, and then it bifurcates into 3 to get a 3-yearly cycle. And if we carried this on, we would see what's called a period doubling cascade to chaotic dynamics. Okay? So once you have a really high transmission rate or seasonal forcing, you get what's called deterministic chaos. And it looks like a random, like a stochastic model, but it's not. You are on a fixed trajectory, which if you knew the initial conditions, you would be able to predict perfectly in the deterministic model. But it's very sensitive to those initial conditions, and just tiny changes in the number of susceptibles and infectives would push you onto a completely different trajectory and completely unpredictable dynamics. Okay, here we're talking about vaccination, and vaccination pushed us down backwards. And again, we saw what that led to is this area of parameter space where there's not just one stable dynamic behavior, but there's 3-yearly cycles, 4-yearly cycles, 5-yearly, 6-yearly, 8-yearly. So the effect of vaccination was to not just reduce the incidence of disease, but to dramatically reduce the predictability of outbreaks. Because rather than just having a nice stable 2-year cycle, there were all of these potential different dynamic behaviors, which stochastic effects and changes in birth rate can switch between. Okay? So we went from a regime where we knew exactly when there was going to be a measles outbreak to the measles outbreaks being completely unpredictable and desynchronized across the whole country. Okay. So going back to the original time series, which sort of motivated this, we can also understand that earlier period of time from 1944 up to 1955, where rather than 2-year cycles, there were annual cycles, because there was a baby boom at the end of World War II, increased the number of births, and it meant that 2-year cycle was topped up and became an annual cycle for a few years before settling back onto the 2-year cycle. Remarkable predictive power of very simple models in this one period in England and Wales, at least for measles. But it illustrates how the vaccination can have these predictable, but also describable, but then potentially unpredictable effects on the timing of outbreaks. We expect vaccination to increase the time between outbreaks, but depending on the rates of transmission in the community and the seasonal drivers, it may make the timing of those outbreaks more or less predictable. And there's only so much we can learn from England and Wales because this was such an extreme case with the school terms and the high school attendance really driving almost completely the patterns of epidemics. One of the questions I looked at in my PhD was, how much can we learn from these models about measles epidemics in Africa and the push towards eradication? And the answer was we basically got everything wrong by looking at these models, because it turned out when we actually looked at the data from Niger, that contrary to what I expected, which was less seasonal forcing, there was actually more seasonal forcing. Not driven by schools, but we think by pendulum migration, actually moving large numbers of susceptible unvaccinated individuals into urban areas, driving very large epidemics, even at high rates of vaccine coverage. Okay. I now want to talk, though, about how a vaccine actually works mechanistically, because measles is the simplest idealized case where you get the vaccine and you're perfectly immunized and you're not going to become infected with the disease. A lot of good vaccines do not work that way, and we need to account for that and factor that into our projections and our modeling. So, in addition to reducing the risk of becoming infected, a vaccine may just reduce the severity of the disease. It might stop you becoming ill, but it might also reduce your infectiousness, which means you get an additional or a supplementary reduction in transmission, even if you don't get the sterilizing protection. We can define and measure different vaccine efficacies with respect to these two modes of action. So these can be thought of as a reduction in susceptibility. So that's how we think about measles vaccination, which I'm going to call epsilon S. But we could have another effect, epsilon I, which is just a reduction in infectiousness. Yeah. Now, the net effect, if we go and do a vaccine field trial and we look at reduction in, or cases averted, is going to be some mixture of these two effects. So from just looking at the action of a vaccine in a population, we won't necessarily be able to tease these apart. Okay? And the reduction in transmission is really going to be key for assessing the effectiveness of the vaccine. So for some vaccines, this can be more important than this is. Okay? So maybe just define what I mean by efficacy and effectiveness. Are those terms which you're familiar with? I said some of you might be, some of you might not. So efficacy is the individual ability of the vaccine to have an effect, whereas effectiveness is what we would measure at a population level. So effectiveness is a mixture of these two things. Efficacy is the mechanistic impact that the vaccine has on an individual. Okay. So how would we model these different modes of action of a vaccine? Well, you might not be surprised. We add more compartments to our model. So if we want to model this additional effects of a vaccine, we can't get away with just shortcutting our vaccinated individuals into the recovered class, because we want to treat vaccinates who are not infected and subsequently become infectious different. So we want to label them differently. They may have a different rate of recovery. It may be shorter, it may be longer. That could actually be an important part of the effectiveness of the vaccine. And And we need to account for the fact that they may have a different contribution to the force of infection. Okay? So we expect the reduction in susceptibility will mean that the risk of becoming infected of vaccinates will be lower. Okay? But a reduction in infectiousness is going to feed into both the force of infection for unvaccinated and vaccinated individuals, because it's going to reduce the contribution of those vaccinates who subsequently become infected to the force of infection. Okay. Does that make sense? Okay. So in the field, vaccine efficacy is typically estimated really in more terms of effectiveness by looking at the relative risk of infection in the vaccinated group relative to the unvaccinated group. Okay, so we can define vaccine efficacy basically as 1 minus the relative risk ratio, which could be calculated simply by dividing the number of cases we see in different groups, or through some survival, any statistical analysis, survival analysis, whatever is appropriate for the type of trial that we have done. So the gold standard would be a double-blinded, placebo-controlled, randomized trial, but it can be any estimate of the attack rate, which is essentially the force, another way of labeling the force of infection, and then comparing it in vaccinated and unvaccinated individuals. Okay? We can do a little bit better than this if we can compare different combinations of vaccinated and unvaccinated individuals to tease apart what the mode of action of our vaccine might be. If we just compare vaccinated and unvaccinated individuals from completely different populations, then that is the direct efficacy that we're estimating. So that's what we would estimate really in that's our epsilon S, and it's what we'd estimate in a phase 1 trial, where we're just seeing if our phase 1 or phase 2, phase 2, where we know the vaccine is safe and we try it in individuals and we compare the attack rate in those exposed individuals. In order to estimate the indirect effects of a vaccine, we really have to wait until we've deployed the vaccine at scale for either a phase 3 or a phase 4 trials. And that's why the indirect effects of vaccination are often considered to be a bonus rather than something that would actually drive our decision as to whether or not to use a vaccine, because we can't really count on them till we've managed to estimate them. Okay. We can estimate the direct infectiousness by comparing the attack rate in unvaccinated individuals in a partially vaccinated population to those in an unvaccinated population. Okay? So we're separating out and controlling for just measuring the indirect effects. More often what we measure is the total efficacy. Okay? And it's important to remember that if we're thinking about taking parameters for estimates of efficacy to put into a model. Okay? If we don't know how the vaccine works, or if we choose the wrong mode of vaccination, we may make the wrong predictions or the wrong projections for what a vaccine policy should be. So it's really just, so this is here setting up the fact that we need to think about this, we need to understand what the vaccine does mechanistically within individuals, and we need to factor that in when we are taking estimates of efficacy to put into our models, if we're lucky enough to have those. My day job is on bovine tuberculosis in animals, and there we are in the unenviable position that we know the vaccine is terrible in that it doesn't have a very good direct protection, and we expect the only benefit that we will get is a reduction in transmission. And so doing any sort of modeling or predictions of what the impact of introducing the vaccine might be from an economic perspective is exceptionally difficult without going to do a rollout of the vaccine, which for various reasons is not practically possible. But we have another option in veterinary epidemiology, in that we can do controlled experiments. And this actually can be a very, very effective way to tease apart exactly how a vaccine works. And in fact, it's probably the minimum that you need to answer this question if you really want to answer it categorically. So we have had a trial in Ethiopia for the last 5 years, which is set up to answer this exact question. It's quite a clever design, which I worked on with Mark de Jong from the Netherlands, where we had 2 groups of individuals in a first phase, where we introduced unvaccinated and vaccinated individuals to cedar animals that were positive for bovine tuberculosis, and then we left them there for a year to allow transmission to happen. And then we collected together all the vaccinate animals and used them as cedar animals for a second group, all the unvaccinated animals as another cedar group. So we're directly comparing the infectiousness of those unvaccinated cedars and the vaccinated cedars, which had been exposed and many had become infectious. And by comparing and fitting a mechanistic model of transmission to these different groups, we could, and in fact we have just recently published the results, which showed that the reduction in infectiousness from BCG was considerably larger than the direct protection, which is fabulous news. And when we looked at projections for transmission within Ethiopian herds, that reduction in infectiousness is in fact essential, at least in model world, to eliminate the infection from herds. The direct protection alone, which was the only thing that had been estimated before, wasn't sufficient or able to do that. So these indirect effects, although they are sometimes seen as a bonus, they can actually be the key to unlocking the usefulness of a particular vaccine, which may be, and it certainly is in the case of bovine TB, the best that we have. But of course, for human infectious diseases, we typically don't know about the mode of action, and we don't really know what the efficacy of the vaccine is going to be ahead of a full deployment. So we're kind of relying on this guy, the expert, to give us some idea of what is sensible to do. So this is where I'm going to hand over to Katie to talk about exactly this type of project, where a manufacturer for a vaccine for norovirus wasn't quite sure what to do with it. And so they asked us if we could do some modeling to help them to target which population. Population's the wrong word. They wanted to target customers, potential customers for the vaccine. So, Katie.
Thank you. Yes. So, yeah, as Andrew introduced, we're going to show a case study on norovirus. Again, why are we looking at norovirus rather than showing you a model of something for an endemic infection? Well, yes, we came across this problem and we didn't really have an idea about how the vaccine was going to work. So when we come onto the model, we kind of covered a lot of bases with it. So a bit on norovirus. It's the most common viral cause of gastroenteritis in humans, and 1 in 5 cases of acute gastroenteritis are attributable to norovirus. It's underreported. There's actually an estimate of how underreported in the UK, which is odd. We don't usually have that. So roughly 1 in 218 cases of norovirus is thought to be notified. That's probably optimistic. There's vaccines in development. I think they're still in development, even though, as you can see, we were working on this a while ago. And while the vaccine was in the proof of concept stage, so we really didn't have much information, we were asked to develop a model on what the benefits of such a vaccine that we didn't have yet would be. So what we did was we developed an age-stratified model, and we estimated it from case notification data from Germany, purely because they've got a really nice data set of case notifications. We also used other information, so seroprevalence studies as well, to get an idea of some of the other parameters going into it, as well as things like this estimate of underreporting. And we also used information on social contacts as well. So what did we do with the model? Well, we set up this. So just bear in mind that this was also age structured, which you can't see. We've got a maternal antibody class. And then we've got our SEIR model, kinda. We've got 2 exposed compartments. That's to capture some of that gamma distributed latent period that we thought might be going on. We've also got an asymptomatic group there. There should be another arrow. So this was our base model structure. With norovirus, people can be asymptomatic. A lot of people can be asymptomatic, and they might contribute to transmission, but at a reduced rate. So norovirus is kind of horrible in that if you're symptomatic, you really know you're symptomatic. It's quite obvious with some of the symptoms you get. But we were expecting that asymptomatic people still contribute to transmission, just at a reduced rate. The infectious, or the ID50, the chance of getting infected being 50%, the number of viral particles you need for that is extremely low for norovirus. So there's quite a lot of what we call fomite transmission, where viral particles end up on surfaces and then are picked up by other people. Defining that is very difficult unless you're looking at particular areas. So for example, if you were modeling inside a hospital, maybe you'd dive into that in a bit more detail. But in the community, we were linking it to direct transmission. So if you come into contact with someone and they've got norovirus, then you've got a chance of getting infected. So our transmission used social contacts to give us an idea of who's coming into contact with who, and then having a risk of infection. So when we put all of this together in our force of infection, we had some measure of social contacts, CIJ. We had a seasonal forcing term, because norovirus is also seasonal, for mechanisms that may or may not be well described, depending on who you talk to. And then we've got the number of infected people, the number of asymptomatic people, and some contribution from the vaccinated people as well. So that was our model without vaccination. And then when we were going to model vaccination, because we didn't have that clear kind of profile of what the vaccine was going to do to a vaccinated person, we essentially duplicated everything except the maternal antibody class. So again, this is age structured. So for every annual age group, we had all of these compartments, except for maternal antibodies. This gives you maximum flexibility. You can look at how susceptible people might be to infection. You can look at their disease progression. You can see what proportion might be asymptomatic if they've been vaccinated. You can consider how long they take to recover. You can also think about whether the vaccine will clear infection. Unlikely, but it might. So you can consider that as well. So essentially duplicating all of the model equations gives you the flexibility to adjust all of those parameters accordingly. If you've got an established vaccine, you maybe don't want to do all of this, because you've got a better idea about how it might be affecting them. Okay. So, as I said, we didn't really know how the vaccine would act. We had multiple vaccination scenarios that we wanted to explore. These were all age-targeted. We've talked a lot about age-targeted vaccination. In the Build Your Own Model section, if you want to talk about other targeted vaccinations, so spatially targeted or looking at different population groups, maybe thinking about zero-dose children, we can definitely talk about that in the Build Your Own Model session. But here we were thinking age targeting. Essentially, kids, older adults, or a mixture of the two. Given that, we had a bunch of assumptions around the vaccine. So we thought about maybe the efficacy is different between children and elderly people. We thought the coverage might be higher in children because it's easy to reach young children than maybe older adults. We assumed the duration of protection was 5 years. That's related to the duration of protection from natural infection of norovirus. This is also under debate. I think it's still under debate. But that was our estimate. That's what we came up with from the literature. And then we went through a whole bunch of different options in terms of the actions. So we had a proportional reduction in symptoms, proportional reduction in infectiousness, susceptibility, and then finally this clearance. So whether you would clear infection immediately if you got vaccinated. Unlikely, but we thought to include it. So once you've got all of this set up, you've got your dynamic transmission model. You end up wanting to explore all of these different combinations, right? So that's what we were going to do. Again, because we didn't really have a steer on which of these necessarily was going to be more likely. So the way we approached that was with a Latin hypercube sample. Again, you wouldn't necessarily take this route if you had lots of data on your vaccine and how it's going to be used, but in our case, we didn't. This gives us a lot of combinations of all of those different vaccine actions and characteristics, and if we explore enough of them, we get a good idea across all of the possible ways that this vaccine can act, what the benefits might be. So essentially, we took our model, we estimated it from the data that we had available, and then we used it to explore all of these different possible permutations on how the vaccine might affect people. So what did it look like? I think it's easier to see over here. So the black lines here are case notifications in Germany for norovirus for different age groups. You can see the nice seasonality. There's weird reporting stuff going on, which I won't necessarily go into. But the blue here are different realizations from our model. The seasonality was also slightly different between age groups, but that's a different thing as well. So we fitted our model, or calibrated it to the data that we were using. Great, now we can start trying things out with it. So we took all of those different permutations, those lots of different samples of all the vaccine action, and then we looked at burden outcomes. So here we've got infections, so that's everyone, including asymptomatic people. And then we looked at, okay, in terms of healthcare burden, what does that translate to? So outpatients, hospitalization, deaths. I should mention that with norovirus, the negative outcomes are more seen for older people. So the severity is more apparent in older people. So if you consider who's being affected by norovirus, even though we'd expect children to drive transmission for all of the same reasons that you might expect for other directly transmitted diseases, the older people are kind of the ones that you see appearing in hospitals and certainly in the mortality data. So we've got bar charts because, well, we've got a lot of potential ways that the vaccine can act, and across our 5 different scenarios, you can see we've got slightly different reductions. So A0 and A1 was just targeting very young children, so you can see that reduces all infections, but really because of the severity of norovirus being higher in older age groups, the scenarios where we included vaccinating older people reduced deaths and hospitalizations a bit more. And then for outpatients, because you still might present as an outpatient, even if you're in a younger age group, it's a slightly different story. So it also depends on the burden outcome that you're looking at. So what did that translate to in terms of numbers? So we estimated overall burden of infection, so that's including asymptomatic infection, could be reduced by about 4.5% overall. If we just targeted over 70-year-olds, it targets a larger number of people just because of the population distribution in Germany when we were modeling. but that could reduce the total number of infections by 21%. And the highest percentage of reductions in infections, 70%, comes as a result of targeting 1 and 50-plus-year-olds. Now, if you were looking at this and someone said to you, or a modeler said to a policymaker, yep, we're just going to target 1-year-olds and over 50s in a population which is skewed towards old age groups, you'd immediately ask, well, how many doses is that going to need? Probably quite a lot. So this is why you explore different scenarios, but maybe you're looking at overall burden averted by different outcomes, and then you might also get asked about burden averted per dose or per course of vaccination given. We also looked at what's most influential in terms of those characteristics and found that it's clearance of infection. That makes sense. If we had a vaccine that immediately moved people out of the infected group, that'd be great. And susceptibility. So are we reducing people's chance of getting infected in the first place? So there we go. What? Do you want to do a mix on the summary, or should I do it? Okay. So there is dynamic effect of vaccination. We've looked at it in terms of birth rates and transmission rates. There's lots more you could look at. Again, we're kind of giving you an introduction to a whole bunch of things. We haven't even mentioned vaccination for vector-borne diseases. It can give both direct and indirect impacts on transmission. And there are different ways in which this works, different mechanisms that can drive this. If we really don't know how that vaccine can act, we can still pull something together in terms of a modeling approach, essentially by duplicating all of our compartments and then thinking about how those might look different for vaccinated individuals. Chances are you're thinking about modeling a vaccine that exists or is in development, so hopefully you've got a bit more information to go on, but maybe not. Even if we do have data coming out, and you can see this for more recently developed vaccines for malaria and things, certainly for R21, where we've got data coming out as we speak, that's going to give you a better idea of what these vaccine effects might look like. And it's unlikely you'll know everything before it comes out, or even after. So maybe we look at sensitivity analysis as well for the things that we don't know. Okay. Does anyone have any questions on this at the moment? We do have a build your own model session, so if you want to talk about any of this or other targeting of vaccinations, so geographically or by different population subgroups, do grab us and talk to us about it. Any questions on this at the moment? Yeah?
Thank you for the presentation. I was just wondering whether vaccination was the only pharmaceutical intervention for this infection.
Yeah.
There was no other treatment.
No, it's a great question. So for those who didn't catch it, is vaccination the only way of controlling norovirus? So a lot of norovirus is quite horrible in that it's got a very low infectious dose. So if you do get it in a hospital ward, or it occurs quite a lot on cruise ships, so if you're thinking of going on a cruise, don't for the norovirus. So one of the big things is that shuts down hospital wards often, and then they have to be thoroughly cleaned with a lot of bleach, and maybe it comes back after that. So that's one of the routes for controlling it after it's already been an outbreak. I don't think there's any antivirals.
It's mostly a
No.
self-limiting
Yeah.
infection. So the
Yeah.
reporting rate that Katie glossed over is U-shaped.
Yeah.
Because adults just don't report it, because they just feel really bad for a few days and then they get better.
Okay.
It's only really a risk for very young babies and the elderly.
Okay, so
It's also it's a really difficult disease to make a vaccine for, and it has exactly the same antigenic drift issues that influenza has.
Okay. So you mentioned very young babies, which brings me to, you mentioned maternal antibodies.
Duration of maternal antibodies.
Yeah.
Oh, I think it was by the first year, end of the first year of life, they were assumed to have decayed. So it was an exponential decay in those maternal antibodies. And I think by the end of the first year, they were expected to be completely decayed.
So these are protective
Yes.
from the infection
Yeah,
until after a year.
yeah, essentially, yeah. Hello.
Very nice presentation on that. I know we've been having a couple of discussion on the role of waning immunity, which is a big topic, but I had just two questions. The first one is, for this case, especially I know the case notifications in Germany, where the population is kind of skewed to an older population. Generally, how does this affect your age-structured modeling and how you use these findings to, for example, extrapolate in other regions? That will be the first one. And the second one will be for the, how's it called? For the vaccine, for the estimates you did, because it was a vaccine coming out for trial, did you get the efficacy or whatever estimates from the company itself, or you had to do this from scratch?
Great questions. So on the population, yep. So yes, the German population skewed towards older age groups. So when we were modelling this with an age structure, we had annual age groups, and then at the end of the assumption that you're going to age annually, we tried to include the population distribution in that. I think the Gompertz function that we had in one of the early lectures was how we defined the mortality in the model, because that gives you this higher proportion of your population in the older age groups. Another route for doing that is simulating per year and using estimates of annual population sizes, so for example from UNWPP, to get your population structure. At each year you move people through the dynamic model, but you make sure that the population sizes line up. Because if you, maybe that's a whole other thing, I'm not going to get distracted on that. If you want to talk more about including age structure in your model and how that translates to using estimates of population per year group, we can come back to that. So yes, we tried to include that the population proportionally is more in older age groups through that. That also affected how our contact matrix came into it, because obviously if we've got larger proportions of people in the older age groups and they have fewer contacts, that translates to fewer contacts overall. So that was it. Your other question was on, did we receive any estimates of efficacy from the group that we were working with, the company that we were working with? No. What we did have was a long chat about this. So we were trying to get an idea of what they knew so far to set up a plausible range or plausible set of assumptions on this. I think we still modelled less than they would have liked us to. They had some, can't quite remember it, some other ideas on this, but this is kind of a reasonable set of assumptions that covered what they thought might be some of the action, but as you can see, it's still pretty broad. And I think things like coverage expected to achieve, this was based on other vaccination activities that have gone on for other vaccines, and how many people essentially that they could get to be vaccinated. So generally higher in children than older people. But, yeah. Any more questions? One more.
Thank you very much for
actually, thank you. So mine is actually looking at other things. Have you considered other things like vaccine rejection? Is this something that should be considered in the model? Also, individual factors like the immunity state, also issues with vaccine itself, whether the cold chain was maintained or not, and also the data that you're getting as well. For example, in Nigeria, we've planned immunization campaigns. We'll be getting very high coverages above 95%, sometimes even over 100%. And after that, after taking a survey, we still get some individuals that have not been vaccinated or some that have actually rejected that were not captured. So how does that really affect the model? Are you considering all these things? Thank you very much.
Yeah, probably not so influential on this model. Very happy to talk about how that plays into the yellow fever model.
Yeah.
So we model a variety of things for yellow fever, including routine immunization, reactive vaccination for outbreaks, and preventative mass vaccination campaigns. A lot of the time we use any information that we can compile on vaccination activities, so sources like WUNIC, the IVB immunization repository from WHO and things. So where you mentioned that some of the campaigns have got over 100% coverage, so we do include that. Sometimes it's capped unless we've got the number of doses. With those inputs, a lot of the time we are saying, okay, so this is the post-campaign coverage survey. We're going to use that as our input in terms of number of people who are vaccinated. On top of that, we also include some measure of vaccine efficacy. So not everyone who's vaccinated, had an immune response. That's still very high for yellow fever. We also include some measure of vaccination misclassification in that. For example, if you're running a campaign in one province, maybe some people have travelled for that, or maybe the coverage that you see within that province on that day might not represent what the coverage is in that province normally, either because people travelled to get vaccinated and therefore have travelled back, or otherwise. So we do include an extra layer for vaccine misclassification, particularly for much older data. It's not really a thing here because we were thinking about, in an ideal world, how would we use this vaccine? What is a plausible range of effect? But it's definitely something that we include for modelling vaccines for endemic diseases. Final thing, vaccine rejection or hesitancy. This is a really interesting one because it kind of is used to cover a lot of things, including vaccine access, which is not really necessarily a rejection. It's just that you can't get to the place to get vaccinated. And that disproportionately affects different groups. So you can see that from DHS data that certain groups are more commonly going to be seen in the zero-dose population, for example. But yeah, maybe vaccine access and hesitancy is a whole other conversation that we could have over coffee. Did you want to come in on?
So this project was a really interesting one in that we were approached to do it before. I mean, they'd done their phase 1 trials, I think, but they had no idea if the vaccine even worked. And we had a very specific remit in that they did not know how they were going to get their money back from developing this vaccine, because their business plan was, we could market this to rich elderly people who are going on cruises. And then I think at some point they worked out how much they would have to charge the rich elderly people on the cruises and realised it wasn't going to be cost effective. And our colleague Caroline Trotter at a meeting sort of said to them, well, with influenza virus, which is very similar, we're now targeting children in order to give the wider societal impact. Yeah, and that would be a much better business case for this vaccine. And better target for it, which they were a little unkeen about because it costs a lot more to do your vaccine trials in kids than it does in adults. So our project was really to just try and illustrate what the potential market or what the potential use of a vaccine might be, which we used as an excuse to do some cool model fitting and interesting stuff. So it was a win-win. But it is a very unusual example, and it's one we pick here really more for the pedagogical learning objectives, in that we cover, it just takes in so many things because we knew so little.
Yeah.
Yeah. I think now we should break, and we've been going for a long time now because we overran, and let's make sure we have a good 20-minute break at least. So what time is it?
11:17. So if we come back at about 11:37.
Yeah, let's say 20 to 12.
Yeah.
So we come back to 20 to 12. We'll go through a couple of the slides on the suggested background reading for those that want to read more. And I'll give a little introduction to the optional practicals, which we have, which you can try, or we can just catch up with other practicals. That's why we have this time in the timetable. All right, let's have a break. Thank you, everyone.